Okay, so good morning, everyone, and it's a great honor and thanks for the opportunity from Dr. McBean to allow me to present some of my ideas about climate change and engineering. Dr. McBean have already mentioned a couple of times that he has been talking about climate change and those things from a textbook. But from my perspective, I want to share some of my ideas about climate change, that what I have done, and particularly as an engineering student or as a future engineer, what you might see in your job in the future in terms of climate change. My name is Albert. I'm a PhD student. My focus is, you can see, is on climate change, but mostly climate change is a huge topic, so my focus is on precipitation, rainfall in particular. So this is a brief outline what we're going to do today. We'll go over the climate change in general. It's a huge topic again. We'll go over some basic science behind climate change. I don't know, how have you perceived climate change? Those three things that what I have done: the rainfall-derived infiltration, inflow, low-impact development. You might already have heard about it, or you will have a course about it. I believe it's Urban Stormwater Design course, fourth year course. Intensity, duration, frequency curves, which is IDF curves, and I'm sure you already know this concept from this course. And finally, we'll dive into something about anthropologic activities and its impact, how human activities have interfered the climate. And finally, I want to wrap up with how do you perceive climate change after this presentation. And I also have slide numbers down to the lower right, so if you have questions about a particular slide, you can note the number down and we can go over again at the end. So actually, it was a long time ago about the topic of climate change. But until 2014, unfortunately, I do not have more updated data after that. Only 42% of Americans believe the fact that most climate scientists think global warming is happening. Just less than half of Americans. And globally, only 51% of respondents in a survey among 16 nations think global change is happening in terms of global warming. And a more recent polling, I believe that is probably 2020 or 2019, shows more acceptance. I don't have exact numbers, but definitely the number has gone up from 2014. So the idea of climate change is not new. It's probably as old as when the US dropped the last nuclear bomb in Japan. So it was a group of visionaries back in about 1945 think man-made increase in the amount of carbon dioxide might cause large global climate changes. Okay, note the wording here, might. They are not sure yet at that moment. They don't have supercomputers, they don't have high-end CPUs, those sort of things. Everything was, they thought. So, climate change, scientists and engineers. How do you distinguish scientists and engineers? And you might get this question a lot in the future again. Like, what do you do different than scientists? Or the scientists will be asked, what do you do different than engineers? Well, engineers are not a subcategory of scientists, that's for sure, because scientists are those group of people, they seek the truth of nature, right? They want to know how things work, like Newton. They've discovered the Newton's first law, F equals to ma, those sort of things. But engineers, we innovate solutions to solve the challenges, right? Scientists might have the most advantage, most up-to-date knowledge about the nature, but they just know it's happening, right? They tell you climate change is happening, but how do you deal with it? They might not have an exact solution, but as an engineer, we deal with all those kind of challenges with real solutions, such as we deal with excessive amount of rainfall, prevent or alleviate urban flooding, reduce infrastructure damage, monitor, predict weather anomalies, and develop models to make informed decisions. And the last bullet point is mostly what I do. And as a water resource engineer, if you accept designing for infrastructures. Mostly you will be dealing with modeling. So now I want you to name 5 facts you know about climate change. Right? So when I say the term climate change, what comes to your mind? Right? You can think of as many as you want. Sure.
Ocean acidification.
Okay. That's a good one.
Sea level rising.
Sea level rising, thank you.
A primary contributor is the greenhouse effect.
Yeah, greenhouse effect or greenhouse gases increase in the atmosphere. Yeah, so there are lots of things that you can name about climate change. So there are just a few things that I listed: global warming, sea level temperature changing, sea level and temperature rising, greenhouse gases, as you mentioned, ice and snow cover shrinking, increasing water vapor in the atmosphere, more frequent heavy rainfalls, extreme heat and cold waves, as we just experienced in the summer, severe weather events, droughts, urban flooding, riverine flooding, lots of things. It's a huge topic. So the 3 things that I highlighted in red here is mostly what we are discussing today. And as an environmental or water resources engineer, that's what you will see in the future in your job, or if you are doing a graduate study. So water vapor in the atmosphere, what does that mean? Right, we're just now going over some basic science behind the climate change. Why climate is changing, and why the water vapor in the atmosphere rising is causing climate change or causing more heavy rainfalls. So this is a satellite image taken in 2019 by a NASA satellite. So this image shows how much water vapor is in the atmosphere at a certain stage, at a certain point. For example, so we are located about right here. Just a little bit dark blue here, so we are around like 20 millimeters reading. So the unit is 20 millimeter. What does that mean? It means at that particular location, if all the water content in the atmosphere gonna drop on the ground, you will see 20 millimeters water on the surface. That's what it means. Okay, so 2019, not too long ago, not just a little bit over 10 years. And now, this is a picture taken in, I believe, 2021, June. So the scale is a little bit different now, and we are located about here. So let me show you the answer already. From 2009 to 2021, at the same location, our water vapor in the atmosphere is increased from 20 to 30 already. It's different scale, so you still see the blue, but the blue scale here is about 30 already. So we are already seeing increase of the water vapor in the atmosphere. Again, what does it mean? Warmer airs holds more water, right? So that's why you feel hot and humid in the summer and cold and dry in the winter. And that's also why your dryer is blowing hot air instead of cold air to dry your clothes, because warmer air holds more water. So, given a volume of air, water content versus temperature, here I present a graph here. In general, as an idea, water content at 20 Celsius is already twice as much as water content at 10 Celsius. Just imagine how much water vapor is being held in the atmosphere at different temperatures. And more water content in the air means we'll have more intense precipitation events and less frequent precipitation, because our air is warmer, so it is able to hold more water. So imagine you had a small bucket versus now you have a large bucket, right? You don't pour the water until the bucket is full. So now, because warmer air is like a larger bucket, so large bucket holds more water, but it pours less. So we have more intense precipitation, but less frequent precipitation. So that's why you get those heavy storms, and that is causing urban flooding, infrastructure damage, economic loss, and sometimes, or every time, you will see life-threatening news heard on the radio. So the work I have done is mostly on those things that I mentioned. So for example, understanding the basement flooding resulted from heavy rainfalls, measuring the rainfall-derived infiltration and inflow. I know those are like terminologies, but I'm sure after today's presentation, you will get a general idea of it, and you will know more about those concepts later on in fourth-year courses, and the performance of low-impact development and more. So those are just like super concentrated summary of what I've done, because I don't want to go into too much details to get you to fall asleep. Why I'm bringing those up? Because those things are particular topics you will be faced in your job in the future. So when you're going to the workforce, you'll be asked to deal with, okay, so how do I, so for example, your employer might want to ask you, say if you are being employed by a municipality, they want to ask you, okay, how do I reduce the risk of city flooding? Or how do I reduce the amount of water flooded on the street after a rainfall? Right? Those are sort of type of questions you will be faced. So first, rainfall-derived infiltrations and inflow. Soil infiltration and water capacity depends on many things. For example, the soil type, clay, silt, those sort of thing, and hydraulic conductivity. Right? Those are just two very basic parameters, and lots of parameters will decide how much water can infiltrate into the soil. So when rainwater reaches the ground, ideally, it has three ways to go: upward, downward, or parallel to the surface. Upward by evaporation, downward by infiltration, or parallel on the surface, that is overflow or runoff. That's what we call. So when water infiltrates into the soil, because we're talking about infiltration and inflow, so we'll look at the downward direction first. When water infiltrates into the soil, after saturation, water still needs to go somewhere, right? So it can infiltrate into a cracked stormwater pipe or sanitary sewer pipe. That is infiltration. Right? That's the word infiltration coming from RDII. The first I stands for infiltration. That's infiltrating into the cracked pipe. And excessive water near the house foundation can be dangerous. And this is where the weeping tiles come into play. Weeping tiles, I'll go into more details about weeping tiles in a moment, because the name doesn't suggest much. Weeping tiles basically is collecting water to prevent it from going near the foundation of the house, and it sends water into the sanitary pipe. So that is inflow. The second I is coming from the water collected by weeping tiles, and that is being sent to the sanitary pipe. So weeping tiles, what does it mean, or what is it used for? So if we're looking at the cross-section of a house, so this side is the house, and this is the ground surface, say it's your driveway. Weeping tiles is usually located here. So weeping tiles are just perforated pipes, and mostly PVC or plastic. It is connected to the sanitary sewer. It is collecting rainfall, collecting water in the soil to prevent it from it going too near to the foundation. Right? Imagine you have lots of infiltration going on here, and without this pipe, those infiltrations, when the water is saturated, sitting around your foundation, that is quite dangerous for a house. So that's why you introduce this perforated pipe we call weeping tiles. And I'm sure you heard these terms a lot. So the water is being collected in the weeping tiles, and then the weeping tile is connected to the sanitary sewer lateral, and then sent to the main sanitary sewer to be treated at the wastewater treatment plant. I want to talk about a little bit about the combined sewer systems. At old days, when we don't have much water going into the wastewater treatment plant, we combine sanitary sewer and stormwater sewer. Right? Imagine those rainfall collected from the air, or just those water from the street, still need to be treated at the wastewater treatment plant. All along with those sanitary sewers, sanitary wastewaters, like from the household, from showering, from dishwashing. I want you to imagine what can happen Because now we already know the more water will be coming from the air, so heavy, intense precipitations, rainfall events. And that for sure will increase the stormwater part, but as well will increase the sanitary sewer, because sanitary sewer was connected by those weeping tiles. Weeping tiles is collecting rainfall water. So with combined sewer systems, there are lots of things can happen. Overflow. It can overflow to the sewer. It can overflow to the wastewater treatment plant. Right? It's a huge pressure on the wastewater treatment plant. And overflow to the river, and unfriendly environment will happen. You will see the sewer backup, those sort of thing at your house, which is not a good idea to have. Back to weeping tiles. Because more and more water is being collected by the weeping tiles and sending into the wastewater treatment plant, and we also know the weeping tiles is just collecting rainfall water. Right? So those water doesn't really need it to be treated at the treatment plant. So more and more municipalities are introducing the program called weeping tile disconnection programs. Right? They give the homeowners some incentive and help them to reconstruct their weeping tiles by disconnecting the connection from their residential weeping tiles to this sanitary sewer lateral. So the sanitary sewer will be handling their sanitary wastewater only, not handling extra amount of rainfall water, which makes sense, right? So the sanitary sewer is only sending sanitary wastewater. That means the wastewater treatment plant doesn't being overflowed. So how much water can a rainfall-derived inflow be? So the bottom line, a little bit lighter line, is a typical sanitary data collected in a community at the London, Ontario. So the bottom line is a typical dry day. So without rainfall, how sanitary inflow look like. The line above it is a typical day, say, so this is September 1st. This is collected on September the 8th when there is a rain. So when it rains, you can see the line goes up dramatically, right? So basically this amount, the difference between these two curves are the amount of water caused by the rain, without the rain and with the rain. So the only variable is the rain. When the rainfall happens, the water inflow increases. But how much? So after some study, we found out when the rainfall happens, rainfall-derived infiltration and inflow at about 34 cubic meters. But however, if we disconnect the weeping tile, we can reduce the amount to 6.8 cubic meters. Huge, huge decrease. So that's why more and more municipalities, or you probably heard from your parents saying, okay, there's a pamphlet in my mailbox. The city want me to disconnect my weeping tile. Why? This is why. Because this is only for one community. I think that community was only about 40 houses. Imagine for the entire city, those single detached homes, how much water can be reduced at the treatment plant. Disconnecting the weeping tile does not only reduce the amount of water being sent to the treatment plant, it also reduces the peak flow time, right? So the time when the sewer pipe is full. So before disconnecting it, the sewer pipe will be full by, say, 5 hours. But after disconnecting it, the sewer pipe will only be full for 3 hours. So we reduce the peak flow time as well. So that gives more time at the treatment plant side to deal with the water. Right? We're not just pouring lots of water all at once. Now we're just extending the time for the treatment plant to give it more capacity to treat the water. So again, why is it important? Because this is one reaction to the climate change. Climate change is causing more rainfall, more water will be collected to the whipping tiles, and more water will be sent to the wastewater treatment plant, which is really not that necessary. More intense rainfall events are expected because climate change, and it is also more economical than upgrading the treatment plant. Right? So I actually got two options. I can ask homeowners to disconnect their whipping tiles, or I can just upgrade my treatment plant. But which one is easier? Which one will cost less? The answer is apparent. And also, most importantly, I think, is the raised awareness of climate change. To people without strong scientific background, inform, motivate, and act. Because people cannot react without knowing it. So we're informing them, and then motivate them and show them the results. Okay, hey, this is really helpful. This is really beneficial to not only your house, but also to the community, to the city, or in large to the entire world. So then you start to think, okay, what else I can do? So we talked about the solution to the downward direction, the infiltration. What about the parallel direction? Right? Evaporation is the part I don't touch. That's another huge part. Many other researchers are doing it. What about those overland flow, the runoff, the overflow on the surface? When water accumulation exceeds soil infiltration, I don't know if you are in soil mechanics or you have already taken it. Yes. So when the water accumulation exceeded the soil infiltration, the soil will be saturated and water starts to accumulate on the surface. And low permeability surfaces will create runoffs, such as asphalt, concrete, and areas of those surfaces are extensive in urban cities. Right? We don't have much really green coverage compared to the past or compared to rural areas. Those low permeability surfaces, that will create lots of overflow, lots of runoff during a rainfall event. And that is the direct cause of urban flooding and waterlogging. Right? When the heavy storm hits, you heard lots of, okay, my house is flooded, my street is flooded. But do you hear a lot of those things in rural areas? Not really that much. How can we deal with this excessive overland flow or those water on the surface? Well, one way is to promote more downward infiltration. Right? But you want to ask, the water is already saturated. How can I promote more? Well, the answer is we increase the water storage capacity of the soil. Right? You can engineer it to a different type of soil or a different type of texture that allow more water storage in the soil or allow more water storage on the surface, like stormwater management pond. Right? You can build more of those ponds, but nowadays land values are very expensive, so that is not really a great option. But we can allow more water to be stored before becoming overland flow. That's one option. So this is where the low impact development come into play. But nowadays, this topic is not as hot as it used to be because there are many challenges and issues with it, and you will see that in a moment. Low impact development, LID, also has some other names. Green infrastructure, GI, sustainable urban drainage, SUD, or sponge city. You heard this name more often in the Asia part. So what is LID, low impact development? So low impact development allows more water storage in the soil because they are replacing the original soil, say clay or silt, which does not hold much water, to an engineered type of soil mixture to allow it to have more storage to hold water before the ground becomes saturated, provide more barriers to prevent water overflow on the surface. Some examples here: rain barrels, permeable pavement, vegetative swell, and bioretention cells. Now you know what is low impact development. Where do you see on campus is a great example for LID. Any ideas? Yes?
I don't know exactly what it's called. I think the Green Griffin Initiative, like that kind of covered bike.
Yeah, the bike rack. Yeah, the bike roof in front of our Thornburn building is the very good example of a low impact development. And also bioretention cells, although the name seems like very advanced, but really those now newly built roundabouts, those huge circles in the center they are actually bioretention cells. Okay, so they allow more water to infiltrate into soil and allow the structure to hold more water. But however, as I mentioned, many things are happening to the LID concept. So that's why it's becoming less hot as before. One thing I do want to mention is who is going to maintain those infrastructures? Right? Like a bike, you ride a bike, but you need to fix some small parts from time to time. But once those LIDs installed, who is going to maintain them? If it's on the city land, okay, the city staff will maintain it. But do they have enough manpower? Do they have enough funding to sustain this maintenance? And sometimes they promote LID on a residential area. Well, the residents will wonder who is going to maintain it. Because those things will become very quickly less effective without proper maintenance. And I say proper maintenance that requires lots of high-end knowledge. Right? You need to be a really expert to know really how to properly maintain the LID. Ring barrel accepted, but one thing about ring barrel, you can already imagine. What if you don't empty the ring barrel before the next storm hits, right? I can imagine some people will think, okay, I want to save the water for next time use. And I don't know when the next storm will come. Well, when the next storm comes, the ring barrel is full. This is pretty much useless. Right? So maintenance is a big issue for LIDs nowadays. So how do we quantify the performance of LID? Will LID solve our problem? If not, to what extent? Right? Now we have LIDs. At some point, it will solve some part of our questions. So how do we measure the rainfall intensity and frequency? Well, we can measure rainfall depth. We can measure the rainfall duration. And we can measure lots of things about rainfall. But how do we make connections between events? And there's a name, comes the intensity, duration, frequency curve, IDF curve. I think you already been exposed to this concept already, so I'll go quickly. So the IDF curve, this is a typical IDF curve for Guelph. What does it tell you? It gives you the time when it's updated, tell you the station name and ID, and the period of analysis. You can see this particular IDF is created based on 52 years from 1954 to 2017. But the updating process for IDF curves are slow because you can see this is updated by 2021, but the data was only used up to 2017. So the process for updating the IDF curve is long because it is a challenging job. And lastly, it tells you the return period. So I know you already know return period, but I still want to question you. Do you really know what return period is? Because return period, when I say 5 years event, 10 years event, it is not very intuitive terminology. So it is a probability. It is calculated using historical rainfall records and provides a method to assess the severity of rainfall event. Okay, now I say a rainfall event has 5 years return period. What does it mean? Or without checking any notes, yes?
It means there's a 20% chance of it occurring in any given year, and on average it would happen once every 5 years. But it could happen once or twice or however many times in that year.
Yeah, I would delete the last part. So it has nothing to do once every 5 years. It's pure probability. On average, yes. But that's where a lot of people, or say lay people, they got lost. Okay, 5 years event. Okay, so it's not 5 years again. It's not 5 years already. Why do I see those many 5 years events? It's not even 100 years. Why do I see those many 100-year events? Because it is pure probability. It tells you this type of event has a probability of 20% of happening in any given year. It could happen a lot of times in any given year, or it could happen like it has 0 occurrence in any given year, right? It's a probability. And each rainfall event is independent. So, how to read this? A rainfall event, say for example, I want to know an hour, 60 minutes duration rainfall with 2 years return period, or the 50% probability of happening. The intensity would be 20 millimeters per hour. Or when a rainfall happens, engineers back calculate the return period for that rainfall. Right? When the rainfall event is 60 minutes and with an intensity of 20 millimeters per hour, and at that given location, I can back calculate what is the return period for that particular rainfall. This is how we measure rainfalls as an engineer. So that's why you heard so many times on the radio, 50 years event, 100 years event, 1,000 years event even. That's why you heard so many news is talking about it. And each municipality has their own guideline to select proper return period when they design different things. For example, if you're designing a bridge, usually you select the rainfall event to 100 years or to 500 years, those sort of thing. But selecting proper return period is important, but also challenging. If you select a small return period for an infrastructure that would last longer than expected, it will cause early failure. Or I can say, okay, I just select the return period as large as possible. Well, do you have that much money to spend, right? So that it could cause over expenditure. So now back to the LID. How do we quantify the performance of our LID? Well, it works different for different return periods, because different return periods, you already see, different return periods means different amount of water from the rainfall will happen. So each LID has its own advantage and disadvantage. We're going to see that in a moment. And also, keep in mind, LID has limitations. Right? It only attenuates surface water. Although you think, okay, I'm introducing more infiltration into the soil already, but they are still considered as surface water. They do not contribute much to the groundwater recharge. I think it's deep water recharge, replenishment. So the groundwater replenishment issue still exists with LID. So bioretention cell. This is a graph I made to tell you how much percentage runoff can be reduced with a typical bioretention cell installed. If we look at a 2-year event, the amount of volume can be reduced by 48%, and the amount of peak runoff can be reduced by 18%. Right? So this line is the runoff volume, and this line is the peak runoff. Right? How do I reduce the peak flow? And the other line is how do I reduce the amount? And you can already see the capacity reduces as rainfall as return years increases. Right? That makes sense because larger the return period means greater amount of rainfall. So this is a table. It's a complicated table, but 2 numbers I want to point out here. So this table basically tells you the bioretention cell versus the permeable pavement. Without LID and with LID, how much water volume can be reduced? The runoff depth measured. So with LID and without LID, how much runoff depth you will have. So for example here, for 2-year event, without LID, you get 21 millimeters, and with LID, you only get 11 millimeters of runoff. Right? That's the amount of water still happening on the surface with LID. So one thing I want to mention here is look at 22.3 here. Under 25 years and 100 years, without LID and with LID. What does it mean? It means if you install LID, bioretention cell in particular, you can effectively reduce the impact of a 100-year return period event to equivalent to be 25 years event. Right? So I'm reducing the amount of water. Where do you see the problem is? Runoff is not eliminated, right? The idea of LID is nice, but even for the smallest return period, you still see runoff, but not that much runoff. Maybe 9 millimeter runoff won't create much problem. That will be drained to the stormwater sewer quickly. But what about climate change? And those numbers are calculated based on historical data, right? So I calculate those numbers based on the past. But we know climate is changing. So when climate changes, the same bioretention cell, its capacity will reduce. So remember, the number was 48%. So before, without climate change, I can attenuate 48% of volume of water. Now, 39. And for the peak runoff, it was 18%. Now, 12%. So from 48 to 39 in terms of volume, from 18 to 12 in terms of peak runoff. So the capacity is reduced because of climate change. So this is a table summary. I'm running out of time, so I'm just going to quickly go over it. So the ratio, the last line, means with climate change, how much your performance will be compromised. For example, the bioretention cell, the runoff volume was 48%, but with climate change, it will reduce to 39%, reduced by 1.23. So it's a ratio between historical data and climate change data. Okay, so I can share this slide with you if you like. And lastly, IDF curves. The change of climate change can be seen on IDF curves. If I draw two IDF curves with historical data and the climate change data, let's see what's happening. So looking at the historical model, a 100-year return period, 106 millimeter per hour at 30 minutes rainfall. That is a 100-year event. Under the climate change, where is this event at? It is now a 25 years event. Right? So with climate change, those events used to be 100 years event, or 0.01, now becomes 0.04. Right? So before, the event has 1% probability. With climate change now, the probability has increased 4 times. So climate change is really about statistics. So that makes you think. As an engineer, before they might not have this much knowledge about climate change, but now you really want to think, what you design today may not be suitable for tomorrow. And you want to design for both today and tomorrow. So last, I want to talk about a little bit about the human activities. So climate change is naturally occurring. So when I showed Dr. McBean this slide, he wanted me to really explain what does naturally occurring mean. Well, naturally occurring means climate change without human activities, human interference, will still happen. So think about the Ice Age cycle, the El Nino cycle. Right? It's naturally happening, but maybe not that intense. With human activities, we are speeding it up because now we have excessive emission of greenhouse gases, industrialization, rapid urbanization, and increased impervious surfaces that creates lots of runoff, and also decreased surface water storage. Right? How many lands are being converted from a water pond to land to be filled with soil and becomes a house property for sale? Right? So we are speeding up. So how do you perceive climate change after this many talk? I want to make a metaphor here about baseball. And this is not originated from me. I got it from a paper. So imagine a slugger who is thought to be on performance-enhancing drugs hits a home run. Okay, then the people next to you ask you, did the steroids cause it? Well, it's really not a good question because you don't know, right? Because he was already a big league slugger already. So he would make a home run with or without drug. You know that. But however, by the end of the season, the statistics shows that he hits more home runs than the past. And now, you know, and turns out he was on the drug. But he was able to make home runs already, but now he makes more. So the steroids is increasing the chance of him to make more home runs. So climate is really statistic of weather. There are severe weather events with or without human activities, but greenhouse gases is equivalent to steroids. It's speeding up, it's increasing the chance of extreme weather events to happen. And climate change is altering our environment. And also, one last thing I want you to think about. The megacity's rapid expansion. Why do you see more heavy storms in the city? Like, say, 10 years ago, 20 years ago. You don't hear that much things talk about heavy storms, flooding. Why? Think about it. The storm itself might not have changed as you thought because there were not many people seeing it. Why? And also, there is more attention being paid to heavy storms nowadays due to social media, those sort of thing. And now, apparently, we have increased flood damages occurring. But however, think about this map here. This is from 1971 GTA and 2016 GTA. Okay? Imagine I have a storm that hits here in 2071. Will this cause much damage? Not really, because nobody is seeing it. It's not affecting many people. But nowadays, if I have the same event happening at the same area, I will receive lots of complaints as a city councilor. Right? My street is flooded, my home is flooded, my sewer is backing up. Right? Because it's not because the storm has changed, it's because the city has changed. So this is a diagram. I want to show the left one. So imagine the size of Beijing. The Asian cities are really expanding really fast. So imagine there's a storm right here. Same storm in 1986 to 2019. The same storm before 1986. I don't notice anything because my city boundaries were here. But now, 2019, my city boundaries has increased. So this storm will get more attention. Okay? So, last fact. From 2087 to 2017, there are 212 catastrophic loss events. Guess how much of them are flood-related? 170? Well, not that much. Half of them are flood-related. And extreme weather-related issues are causing lots of money in terms of insurance payout. And the two storms, in particular in 2013, in Toronto, that cost the insurance company $1.6 billion, and Southern Alberta, $1 billion. So last word about climate change. So climate change, it's a science that is still developing. It's not complete. But however, it is already extremely useful and informing. So we want to make informed decisions as an engineer, and we want to design now and future. You don't want to design something without considering climate change, particularly those public infrastructures. And again, public awareness and involvement, we really need those to increase our odds, increase our funding to build more sustainable, resilient infrastructures. And also, very important thing is you want to recognize the barriers and know your limitations as an engineer. You cannot solve everything. Something will definitely happen and it's inevitable, but it's not end of the world. So know your barriers and know your limitation. And thank you very much for your attention. And this is my contact.